that you can contribute at any level at this in this experiment. Okay, so I don't think we need this, but then we started with, as Ajay said. So I used to be working on computational condensed matter physics. Then I moved into high-energy particle physics. Then I did high-energy particle physics. But I also have multiple interests across the board, and I would always encourage you as students to keep your base broad. Don't just become the specialist from day one. Try to be a condensed matter guy. Try to be a quantum computing guy, try to be a handy physics guy, and then of course you'll specialize at the end of the day. But try to keep your base broad. Okay, so for example, in my current interests, I work on the CMS inner tracker module assembly and heat extraction. I work on heat spare production at CMS. I work on actually building the prototype CMS detector in which the CMS modules are mounted. This actually is closer to aerospace, actually. I also work on advanced microchannel refrigeration for chip cooling and also for military purposes. I also have an initiative in quantum computing for high-energy physics. I gave a talk yesterday at IIT BHU on the quantum computing aspect of my life. I also have interest in AI that I've pursued with engineering departments. So I do a lot of different things. So today we're going to mainly talk about basically the module assembly and also a little bit about the Higgs boson. Okay, so here's a brief outline of my talk. So we will briefly talk about what the Large Hadron Collider is, what the CMS experiment is, then we'll talk about the Higgs discovery itself and also subsequent precision measurements that we have done with the Higgs boson. And the second half of the talk, this is more hardware related. The first part is theory related. The second part is the thermal design of the CMS inner tracker. So basically the CMS detector is undergoing an entire phase of upgrades where the CMS is going to be made a lot more powerful, which means it emits a huge amount of heat, the next generation. So it's like if you buy a new computer, right? So the newer computers will have more powerful CPUs. More powerful CPUs means more heat generation. More heat generation means much more clever ways to heat extract. So same sort of thing. So we'll talk about the dangers of thermal runaway, the design that we have chosen, and student-run experiments that can determine what materials we should use. Alright, so let's move straight into the discovery of the Higgs boson with a compact muon solenoid. Okay. So the Large Hadron Collider at CERN is a particle accelerator that sits at 100 meters under the soil surface between Switzerland and France. And there are basically two particle colliders, particle accelerators out there. One that is taking the beam clockwise, the other one that is taking the beam anti-clockwise. And they are interacting in 4 interaction points. Okay. And for example, here's a picture of the LHC being repaired during 2008 when this happened. So these beams contain protons in bunches of 180 billion. So it's not like the beam pipes have a continuous stream of protons. No, it's not like that. It's just a bunch. It's pulsed. And in each bunch, there's 180 billion protons. And these, so you can imagine there's bunches coming from the other side as well. And these bunches cross every 25 nanoseconds. And when the bunches cross, only a certain fraction of the protons will actually collide. Out of 180 billion protons, so you can say 360 billion protons, 180 from one side, 180 from the other, around 40 protons collide. Because most of the protons actually are transparent to each other. They are interacting through quantum chromodynamics, and I'll discuss exactly what the interaction looks like. So only a very small fraction will actually collide. So what happens? So when the beams collide, the kinetic energy of the protons turns into matter in a certain way. It creates exotic particles that reveal the mechanisms at play in the first picosecond after the beginning of the universe. That is 10 to the power of minus 12 seconds after the beginning. And if you actually talk about the beams, so how much energy do these beams actually have in terms of all the protons? It is almost like 2 fighter jets going at cruising altitude in one beam pipe. and the beams are collimated to 20 micron radius beam. So it's like way thinner than a human hair, containing tremendous amounts of energy and then crashing into each other. So that's why you can go back to that kind of level of. Yes.
This proton carries 6.5 GeV.
Yes.
So that contains a rest mass as well as only kinetically.
It contains the rest mass of a proton is how much? 1 MeV, right? So it's like hardly 1 GeV. So it doesn't matter. Doesn't matter. Right. So yeah. So mostly kinetic energy. Right. Okay. So do you guys know what tera-electron volt is? Okay. It's a unit of energy. 1 electron volt is the amount of energy it takes to take 1 electron across 1 volt of repulsion. You can think of it that way. Okay. So obviously it's not an exaggeration to say, okay, so the 4 interaction points are instrumented with these 4 detectors: the compact neon solenoid, the Atlas experiment, the Alice experiment, and the Large Hadron, and the LHCb experiment. I work on the CMS experiment, which is a general purpose detector, which means it can detect any physics in general, new physics that is coming. Atlas is also one of our competitions, and they are also a general purpose detector. Alice and LHCb generally focus on heavy ion physics and very specialized things that they want to find out. So it wouldn't be an exaggeration to say that it is the most ambitious particle physics experiment of our times to unravel the mysteries of unification, dark matter, and even the origin of matter itself. So now let's come to the CMS experiment at the Large Hadron Collider. So the compact neon solenoid experiment is what I like to call a cylindrical onion of subdetectors. So it is layers after layers of detectors that is made out of. So the innermost layer out here is shown in blue is called the tracker, and that is made out of silicon detectors. And this is the part that we will talk about in the second half of the lecture, where we talk about upgrades to the tracker. So outside that, in the yellow, we have the electromagnetic and the hadronic calorimeters. Okay? There's the yellow, and then there is the white part. Right. Then there's the solenoid, there's the magnetic field, and then outside that in red, out here, are the muon chambers. They detect muons. And so this is a graphic of all the particles that we can detect. So for example, the CMS detector can detect a muon. Okay? So the part of the muon in the CMS detector will go right, so the collision is happening right in the middle, and the muon will go straight out all the way, and it will basically put energy deposits in the outermost chambers. Okay? And also, the muon will also make energy deposits in the tracker as well, because it's a charged particle. So can anyone tell me why this looks like a curve? Why not just a straight line? What causes a charged particle to curve? A magnetic field, right? So there is a very strong magnetic field out here. It's basically a solenoid, and you can think of it like this. It's basically the magnetic field is pointing outward out here, and it's pointing inward in here. In fact, so you can see that. So actually, it's pointing outward here, inward here. Okay? And it's a 4 Tesla magnetic field, which is a very, very high magnetic field. So the reason for having the magnetic field is precisely to make these particles bend. And if you can make the particles bend, you can infer how much momentum there is in the particles. For example, if you have a very high momentum particle, it will not bend as much. It will try to go as straight as possible. If you have a low momentum particle, it will make a big circle. So by actually seeing this bending radii, you can infer what the momentum of the particle is. And also you can see these are calorimeters, these are scintillating calorimeters, where some particles are going, and especially, for example, these particles are basically charged hadrons and neutral hadrons, so pions and neutrons, will go and crash into this, and the energy of that particle can be measured completely. So in principle, you can measure the momentum of things and the energy of things, and this will come in handy later. Yes?
Could you say something about why muons are so important?
Right.
Why not electrons?
Right. So, yes. So that's a very good question. In fact, in the name of the experiment itself, we are talking about muons. So why are muons so interesting for us? Electrons are also, of course, interesting, can anyone tell me why muons are interesting for us?
Because they are pretty.
Yes, so what? Yes. Now, do you guys know what is Bremsstrahlung? Braking radiation. So the heavier the particle, the less amount of braking radiation it can produce. So if you actually have an electron, if you have an electron coming out of here, the electron will, because it is going in a curved trajectory, the electron will constantly emit photons and it will basically become very slow. And so you can imagine the original momentum of the electron is no longer the final momentum of the electron after a few such emissions. So it's actually harder. So basically we're trying to back calculate what happened in the center. So if you look at an electron, it already lost like 90% of its energy. So how can you then go back and say what the energy was? It's much harder. With muons, you're not going to lose any energy. It's a very sharp object. Okay. So that's why we are actually using the muons for a lot of the Higgs detection, because the momentum is not degraded. You can literally just take the momentum of the muon and without any correction, very little correction, just say, okay, that actually came from that momentum came from the Higgs itself. Okay. So that's a very good question. Okay. So this is not the only thing. So like I said, the protons are colliding at 40 megahertz. So I said 25 nanoseconds. 25 nanoseconds corresponds to 40 megahertz. So if the protons are colliding at 40 megahertz, this generates an immense amount of data. But unfortunately, most of the data is actually known physics. Interesting, it's, well, 50 years ago it could have been interesting, not anymore. So this is basically QCD physics, it's known physics. So we actually use two layers of triggers to identify interesting events. So what is a trigger? So a trigger is basically, you can think of it as a software system to determine whether or not an event is interesting enough for us to keep it, to store it. Because if you think about it, if you're generating that amount of data, you do not even have forget about computers, you do not even have the storage tape to store it. We literally store it on like magnetic tape. We don't even have hard disks. Okay, hard disk comes later. First we just store everything on a magnetic tape because that's the most densest form of information storage you can do. Okay, so at this stage you can't even do that. So we have something called a level 1 trigger. What the level 1 trigger is doing is it is observing at a very coarse rate the particles that are being seen by all these detectors, and it's saying whether or not the particles have a sufficient energy so that that event can be interesting. 99% of this is going to be very soft particles coming. We don't care about those guys. Suddenly if you see a very high 1 GeV muon, then you say, okay, that event I want to keep. So that is the role of a trigger. So we have a firmware trigger, and by firmware I literally mean FPGA, like firmware. And then so that brings down the data rate from 40 megahertz to 100 kilohertz. And then there is another level of trigger which is more sophisticated. So at this L1 trigger, you cannot really do so much analysis. You have like just 25 nanoseconds to finish the analysis. Okay, so you can only very like rough cuts, like okay, is it greater than 40 GeV? Okay, chalo, keep it. Okay. Then the next level of trigger is actually, it uses AI and all of this stuff to actually say whether the event is interesting. And that brings down the event rate from 100 kilohertz to 1 kilohertz. But this is not the end of the story. Beyond this point begins the actual physicists and the students who will take all the data and then try to find the most interesting events. Okay, so let's have a quick aside before we actually go into the Higgs boson and what we are doing. So the question is, what is the Higgs boson and why do we care about the Higgs boson? So I wasn't quite sure exactly how much you know about the standard model, so I just wanted to quickly go over it. So we have now a model of physics that basically explains more or less everything that we have observed. Okay, and that is called the standard model of particle physics. And it is made out of two things. It is made out of the matter fields and the force carrying fields. Okay. So of the matter fields, we have so the most familiar is going to be this section. So there is the electron, which we discovered a long time ago, 1800s, 1897 electron. Okay. And then we discovered more recently, 1967, that the protons and neutrons are made out of up quarks and down quarks. And then in 1956, to basically fix some momentum measurement, we had to postulate something called the electron neutrino, and the reality of the electron neutrino became more clear as the years went by. So this is called the first generation of matter, and this is basically what everything that you can touch and feel is made out of. That's it. Okay, so electron, upward and downward. Turns out there is actually another generation of matter which has the same properties as the previous generation, except it's a higher mass. And it's an absolute mystery why that exists in the universe. In fact, when the muon was discovered, the person who discovered it said, who ordered that? Like, why did God make that? We don't know. And then later in 1974, 2000s and all, we discovered another copy, a third generation copy as well. And beyond this, we have found nothing. There is no fourth generation. And in fact, there is like quite hard constraints that there is no fourth generation. But why we have three generations of matter, if you can find out, you know, there's a Nobel Prize for you. Because we don't know why that is. Okay, so, and these are the particles that make matter. Now then there's the particles that hold it together, the force carrying particles. So you can say that the four main forces in the universe. One is electromagnetism, right? Then there's gravitation. There's the weak nuclear force and the strong nuclear force. And so these are the force carriers of those, and what I mean by carrier would be clear if you take a little bit of quantum field theory. It's basically a quantum of a vibration of the field that does the radiation. So there's a photon, then there is a W boson. So the W and the Z boson are quanta of the electric force, and there's the gluon, which is the quanta of the strong nuclear force. So having found these, and of course the final one is gravitation. Okay, I'm going to keep that completely out of the discussion because as a particle physicist, we don't know how it works. Okay. We haven't quantized it yet. It's a harder work doing that. So having found these force particles, we have there's a long-standing quest for the unification of the forces. Okay. So of course, Sir Isaac Newton discovered that celestial and terrestrial gravitation were unified into the law of universal gravitation. And of course, we then realized during Maxwell that electric and magnetic fields forces were unified into electromagnetism, and the quantum of that is the photon. Okay. And then finally, we had the Glashow-Salam-Weinberg theory of electroweak unification that showed us that the electromagnetic and the weak nuclear forces are actually different aspects of the same force. The only problem there is that the photon is massless, whereas the W boson and the Z boson are massive. In order to make this distinction, you needed something like a Higgs field in order to break the symmetry between them. And this is where the Higgs field was necessary. And it turns out this is the only field that is not, that is a boson, sorry, it is a boson, but it's not fermionic and it's not spin 1 either. It's not spin half and it's not spin 1. It is actually a spin 0 particle. Okay. So the Higgs field interacts with all matter particles in proportion to their masses, and it generates mass, and that's why we are interested in the Higgs boson. So basically we can say the Higgs boson ultimately ties the Standard Model together. It may not be clear to you if you haven't gone into the Standard Model, but you cannot describe the Standard Model without the Higgs field. It's just not possible. So the question is, how do we generate them? How do we generate Higgs bosons at their age? So let's get into what actually happens. So yes?
Higgs field is part of matter.
No, it's its own field. It's not, you cannot call it matter because matter is made out of mostly fermionic fields. It has to have spin half. Higgs is spin 0. It is completely exotic. In fact, some people will say it's actually some sort of a force actually. So, it gives inertia to all the matter, all the material, all the matter fields, and there is a way in which you can actually think of the Higgs as a fifth force in a certain way. But I don't want to go into that because that starts controversy.
But how the Higgs get mass? It provides mass to other.
Right.
But just to start with, how Higgs get mass?
So the Higgs is the only field. So if you actually write out the quantum field theory of this, you cannot write a gauge invariant mass term for any of the other fields. Only the Higgs field can actually write that term. And it is not that it's self-interacting or something. The self-interaction does not give you the mass in the Higgs. It is related to the mass of the Higgs, but it's not the real. So it is the only term where
it's mathematics, but physically to start with,
okay.
how Higgs get mass? Because you are saying that all the mass is provided by Higgs.
Yes.
With the interaction with Higgs. But
yes.
Higgs himself, where from getting mass?
Yes. So Higgs. Okay. So how do do I see this? So it is sort of self-interaction. It is Higgs interacting with itself, you can say that. Well, the question of where things get mass, that is also a very interesting question. The question is, why do people even ask this question? Like, why can't you just say the electron has mass? Electron has mass, period, that's it. So it's make it. The thing is, you cannot actually write this mass term in the Lagrangian. Okay? So the mass term for the electron, you cannot write it. Because if you were, so how would you write a Lagrangian for the mass term? You have to write something like mass of the electron times the wave function mod square. This wave function mod square is not gauge invariant, and that is not x2 invariant, and that is the major issue. Okay, but with this is because this wave function of the electron is fermionic. It has a Dirac structure to it. So that's the issue. And I understand this. Unfortunately, this becomes math. It's not.
Mathematically, your argument is fine because you can write a mass term of Higgs gauge invariant.
Right.
Yeah, but physically, I want to understand.
Right.
That's not very clear.
Yeah. It's just there. It's just there.
It is self-interaction.
It is related.
Normally, it is said that 5-4-2. 5-4-3 is realized.
He is mentioning that self-interaction will not provide.
So self-interaction, and there is also the vacuum expectation value of the Higgs. So these two things come together under the mass of the Higgs term. So both of these actually contribute to the mass of the Higgs. So there's two things actually. Anyway, so let's go forward. So here's a cartoon of what actually happens during the collision. And I've tried to get away from the Feynman diagrams. Basically what I'm showing is basically from the Feynman diagram, but I'm actually showing it hard. So here's the proton out there. So the proton is there are two up quarks, one down quark, and they're all connected to these strings that are basically gluonic strings. And here's another proton to the left. And they're traveling at 99.99991% the speed of light. That's carrying 6.5 eV each. Okay. So as they come together, so they will come together. So this tremendous energy allows them to overcome their mutual electromagnetic repulsion. They are both positively charged, so they should in principle repel. So in order to get them close enough so that the quantum chromodynamic force starts to click on, you have to have sufficient energy to go in. And this allows their quarks and gluons to interact via the strong force. So as they come together, a gluon begins to develop from one quark of the proton to the quark of the other proton. And as they begin to come apart, as the protons are going right through, this gluon string will begin to stretch. Okay. And there's a very interesting thing called quark confinement, basically. So as you begin to increase the string, you can think of it like a rubber band. Okay. You're increasing the energy. At some point, it's going to snap. So what happens at the moment of snap is that you have a top anti-top pair production that is basically pulled out of the vacuum. Okay. So do you guys know about pair production? Like in general, there's always E plus E minus pair production happening everywhere. Okay. If any volume of space has energy, it will make TT bar. So it basically makes a TT bar. It will make a particle-antiparticle pair. It will come out. And this TT bar pair, because it is heavy, or T stands for top quark. Top quark has 172 GeV of rest mass. That is about the size, the weight of a lead atom, almost. So this is a very heavy particle. Heavy particle means it interacts with the Higgs more, because the mass of the particle is determined by the interaction with the Higgs boson. So a top has the highest mass, so therefore it interacts with the Higgs boson. So what happens is the Higgs actually radiates from the TT bar loop. Okay. And then the Higgs itself then again generates a TT bar pair again itself. And this will become clear from the final diagram. I'm actually drawing out exactly. And then this TT bar, top quark pair, will decay into two photons. And these two photons are what you can actually see in the CMS detector. And then the big question is, okay, there will be a lot of photons coming out here. How do you know these two photons came from the Higgs? We'll come to that next. And so here is a picture of the Feynman diagram. So those of you who have actually taken quantum field theory, you will know a little bit about it. This is Richard Feynman. And this is the relevant QFT final diagram that shows basically the process I showed by carbon. So yeah, so you have two photons that can be observed with the CMS detectors, electromagnetic alert meter. Okay. So now the question is, okay, now you have two photons.
And what is the time scale?
This is less than like femtoseconds. It is almost instantaneous. There is no time lag. Okay. So now the question is, okay, you have two photons. You will have thousands of photons there. How do you know two photons are coming from the Higgs? Okay. So in order to find that, we are going to invoke the most famous equation of special relativity to understand how this is true. So this is E equal to mc square. This is also true for a Higgs boson. It's true for a brick. It is true for a planet. It's true for you and me. It's true for a Higgs boson. But you know this is not the full formula, right? So the actual formula is E square equal to P square C square plus M square C to the power of 4. That is the full formula of special relativity. Okay. So when a Higgs boson decays into two photons, the energy of the Higgs boson will get distributed to the energy of the photons, right? So half of the energy of the Higgs boson will go into the one photon, the half will go into the other. Also, the momentum of the Higgs boson will be the vector sum of the momentum of the photons. Momentum as vectorial, energy is the same. So therefore, if you were to add the two energies of the photons, E1 plus E2, okay, so you have two photons. You add the energies up, you have E. Okay. Then you do the vector addition of the photon's momentum also. That will be P. So if you were to take the square root of E square minus P square C square, this should peak at this M square. Okay. And this M should be the mass of the Higgs boson, basically. So if you have a huge set of photons, let's say you have 100 photons, and you pair every photon, you try every possible pair. Okay. There will be some pair in which suddenly you will see this comes from a straight peak around here, 125 G. Okay. And so that is basically our clincher for how we get the Higgs boson. But now, of course, life is not so simple. This is not going to be a perfect detector, CMS. When you measure the energy of the photon, it doesn't actually, suppose you get, I don't know, 10 GeV. It doesn't mean 10 GeV. It could mean 9 GeV, it could mean 11 GeV. There's always some spread. And that comes from the detector resolution, how well you have made the detector. And it doesn't even matter of technology. No matter how good your technology is, you will always have some uncertainty. Okay? So you will never have a sharp peak like that. What you will always have is some background under it. Okay? And this spread is called the detector resolution. Then there is another thing. So a cornucopia of other processes also produce pairs of photons in proton proliferation, and their invariant mass will not peak at the Higgs mass. And these are called the background processes. So actually, what you will have is a huge sea of background processes on which there will be a small peak of Higgs. Okay. And us being able to distinguish the peaking signal on top of the background uses a huge amount of statistical methods and simulations that tell us we are doing the right thing. And this is ultimately what a PhD in physics will be doing, spending most of his life trying to figure out the signal over background of this. Okay?
Sorry for the interruption.
Yes.
But what should be the range of photons? What should be the range of energy?
Yeah, so that
top energy for top, when they come together.
yes.
And they produce, for example.
Yes, so the range of energy will be half the mass of the Higgs. So
Then half the mass, what is the experimentally, what is the value of that energy?
it's around 60 GeV.
160.
60. Because mass of there's 125. So 125 half is 60.
So like when we detect large number of photons are coming,
Yes.
maybe photon collision, maybe some other collision.
Yes.
So you give a sort of
Cut off. Yes. So I didn't want to talk. Yeah. Yes. So that's another very important point, because you will have a lot of soft photons, and the soft photons are basically background. They don't mean anything. So you have to have a cutoff to say, okay, I will only accept photons more than, let's say, 40 GeV. That will at least bring your background down by a lot. And then once you take things above 40, then you do the mixing, matching, do the analysis beyond that point. So 60 GeV is typically the energy of these photons.
Another clear.
Yeah.
How do you make sure that Higgs is decaying into up and empty cloud?
Oh, you know, so it does everything. So there are other decay channels of the Higgs as well. So everything will have its own branching fraction. So the Higgs going to photon has the highest branching fraction. So as I said, so Higgs going to photon is not the only decay of the Higgs. Okay, it is the most dominant decay of the Higgs. There are other decays, and I'll come to that in the next slide. Okay, so every decay has a certain percentage, a certain frequency at which it will occur. Okay? So this will occur about 70% of the time. There's another 30%, so it goes into ZZ. So Higgs will often decay to 2Z boson. Why? Why Z? Why Z boson? Why not anything else? Anyone have any idea?
Zero charge. Zero charge.
Zero charge is one thing. High mass.
High mass.
So anything that is heavy, Higgs likes that. Another important one also is Higgs to BB bar. Okay. So bottom quarks. Again, bottom quarks are also heavy. Okay. Several GeV. Not 172, but Higgs to BB bar is actually hard to observe, but we have observed that also. Okay. A lot of people also spend a lot of time on that. So this is the easiest thing to explain. Okay. Higgs to BB bar is a very complicated analysis to try and explain. Higgs to ZZ is also a complicated, not so much, but still it's a complicated analysis to explain. This is the cleanest one I could explain. So yes, so when we study the Higgs, we have to find out that it is matching the theoretical frequency of the different decay products, right? Because if we have a theoretical estimate how much it should be. If it is not, then it's not the Higgs. Something else is happening. So these things will be okay. And so then finally, when we actually made the discovery, and so this is CMS 2020 result, you can see it's not much of a bump. But what you can see is that the uncertainty bars are also very small, which means this is a very real peak. You can see this is a magnified version where they took away the background, subtract the background. So we always express our results in terms of statistical quantities. We say the significance of the result. So what does significance mean? The significance of what we said is that we have a 5 sigma discovery. What is a 5 sigma discovery? A 5 sigma is means that you know what a bell curve is, right? A central limit theorem curve, right? It's a Gaussian curve. So you know what is the probability of getting something at 5 sigma, like 5 standard deviations of it? It's very, very small. Right? 3 sigma 99%, 2 sigma 68%. 5 sigma is very small. 5 sigma is 1 in 3.5 million. What this is saying is the probability that you had a random fluctuation do that is 1 in 1.3.5 million. Okay. There's always a probability that it can be a random fluctuation. But the probability that such a thing can happen is 5 sigma, 1 in 3.5 million. Which means it is pretty clear that this is not a fluke. This is not a fluke. Okay. So right now we have obviously, so this is in 2012. Before, so that is the standard of physicists. Okay, 5 sigma. 5 sigma means it's a discovery. Less than that it means it's a suggestion. Right now it's almost a 7 sigma. So it's like beyond. I mean it's there. It's not a question. Okay. So right now we are spending our time measuring its properties of the Higgs boson, like the mass to a higher precision. We are measuring its spin and interaction with other particles. So as I was talking to Professor, we were talking about the mass of the Higgs. So the mass of the Higgs also has theoretical estimates for what it should be. So if there is a deviation from the mass of the Higgs, that is indicative of new physics that we haven't thought about. Okay? So you can have new supersymmetric particles that would make the Higgs mass deviate. But if it is exactly what we think from the theory, then there's no question. There's nothing else out there. So this is a quick summary, for example, and you will see a lot of these plots if you encounter particle physics. So here is a combination of 2 different Higgs modes. So there's Higgs to gamma gamma taken from run 1, gamma gamma means photons, and then this is Higgs to ZZ going to 4 leptons. And you can see these are the uncertainty bars, and you start combining all these measurements. And then in 2016 we had more precise measurements, and so then finally we made a full combination. This was very recent paper actually, 2020. So by combining the Higgs to ZZ channel, which is also called the golden channel, because this has muons, and I said why the muons are very sharp. You cannot make a mistake with muons. Okay? So by combining the golden channel and the most common channel, by combining these two, we measured the Higgs mass to be 125.35 plus minus 0.15 G. So this is a pretty high precision measurement right now. Okay. So this is all I have to say about the Higgs. I'll go a little bit faster. I think we are going a little slow. So this is all I'm talking about the Higgs. So now, as I was saying, so at Purdue, we are beginning to upgrade the CMS detector. Why? There are many reasons. So now we have to make higher precision measurements of the Higgs boson, which means we are now colliding at higher frequencies, the protons. We are looking for any anomaly, any deviation from the standard model to give us some hint of what lies beyond the standard model. Okay. So the LHC is actually increasing the number of protons from 180 to 230 billions, and we are also making the beams even closer, okay, even sharper. Like I said previously, it was 20 microns. Now it is around 15 or 12 microns thinness. So you'll have more protons that will increase. So I think the proton-proton correlation will increase from 40 to 200. Okay. So we will be taking a lot more data. Now that's the LHC people are doing that. Now CMS people, we have to start to keep up with this, because what will happen is there will be a lot more particles coming out, so the CMS detector has to keep up. So basically, this innermost tracker is what I was talking about. So this part is magnified out here, and you can see this is actually what the detector looks like. So this is the tracker detector. This is the forward side of it. So this is called the tracker barrel pixels. This is called the tracker forward pixels, and this is called the tracker end cap pixels. And you see these little green rectangles. The green rectangles are the modules that are observing any charged particles going through. And these are basically like a CCD inside your digital camera or even in your phone. It's basically that. There's a difference between the commercially available ones and ours. With the commercially available ones, you can calibrate a single column of pixels. With ours, you can calibrate every single individual pixels, and we do that to get the highest possible detection ratio on all this. So this tracker, inner tracker, so what this does, it basically allows us track seeing and secondary vertexing. So being able to use this detector allows us to observe the top quark events better, bottom quark basically, and gives you a very good probe into the next level of physics. So these detectors are being made with higher granularity. What does that mean? So you know about megapixels in cameras, right? So 10 years ago, you could maybe get 2 or 3 megapixel camera. Nowadays, people don't even blink an eye with 30 megapixels, like 20 to 30 megapixels. What does that mean? It means there is more pixels inside the chip. Okay? But that comes with its own backdrop. Okay? You need more power to run these things because you're powering every single pixel. More power means more power dissipation as well. It will get hotter faster. So if it gets hotter, so with high granularity comes great responsibility of taking away the heat. Okay? So this is where, for example, with my students, I contribute to the module assembly, the thermal design, and also the carbon fiber fabrication of this structure. So this inner tracker is a very complex system with many opportunities to contribute even right now. There's the electronic system and all of this. So this is what the pixels look like. So basically a pixel detector, what is a pixel detector? It's basically a diode. It's an NPN diode, but it is connected in reverse bias. So do you know, so what is reverse bias? Does current flow during reverse bias? Can current flow? It can flow but very tiny. Okay? So the flow that happens is called leakage current. Right? With forward bias, yes, you will always have. With reverse bias, it will have slight amount of leakage current. Now, what we are betting on is if you have a charged particle go right through, it will kick some electrons and holes free inside the depletion region. And if it kicks that apart, you will get actually a flow of current will happen for a very short amount of time. And this is the principle with which we are observing charged particles in our detector. It's a simple explanation. It's basically a reverse biased diode. Okay. Okay. So, oh God, that's already started. Anyway, so the module is built out of 204 chips that's been connected to macroscopic electronics. So this is, for example, the chips that we are making at Purdue, and all of this is made by students under my guidance. So, for example, so this involves a lot of robotics. Okay. So, a particle physicist has to know everything. That's what I tell them. You have to know everything. It doesn't matter. You have to know robotics. You have to know electronics. You have to know theoretical physics. You have to know experimental physics also. Okay. So, no. You cannot say, oh, I don't know how to write this software. Okay. You have to learn. So, this, for example, is showing a very high precision picking up and placing of the chips. And then, so we do this with the students together. Purdue, so for example, Purdue, where I'm leading, we are talking to multiple universities, and we are leading the production of these chips for the entire collaboration. So we'll make about 2,000 of these chips out there, and that's what the final chip looks like. And so here you can see the chips are being wire bonded. Okay, so these are all, you would think these are all commercial processes. But if you actually go to a commercial center like Mitsubishi or something who do this, they will take away your entire grant money of CMS. Okay, so we have to learn to do these ourselves in the physics department.
Silicon.
Yes, silicon detectors, right? So okay, so now I'm coming to the challenge of heat dissipation. Okay, so I chose heat dissipation. There are many challenges of electronics. There's challenges of like biasing. There's challenges of readout. Heat dissipation is something that I think kids will understand easily. Okay. So, as I said, the sensor is reverse bias. Okay. Now, here's the thing: radiation always damages the lattice of the PN junction, and this increases the baseline leakage current. So, if you have a reverse bias diode, okay, and you give lots of not X-rays, but like hardcore like neutrons, protons, eventually the thing will start to degrade. It will no longer be a diode in a certain way. Okay. The diodicity is already dead. So once the diodicity dies, that means the current will start to increase. If the current starts to increase, it means it is getting hotter. If it is getting hotter, that means it will become more susceptible to radiation damage, right? Because the jumping will, the activation energy is going to get lower, right? So the leakage current grows with temperature, and so without adequate cooling, you will destroy your entire detector. It will completely burn up. So this is what we call thermal runaway, and the process that I discovered, that I said, it's a positive feedback process. Okay, so cooling becomes a very important part of our system.
In that formula, what is the EA? EA is what?
It's the activation energy for some.
Temperature.
It's an activation energy.
So it's like semiconductor band.
Semiconductor band gap, right?
And sorry for the question.
Yes.
But is there reason that why we choose silicon, for example? Why not germanium?
Germanium is okay. That's a good question. So silicon, first of all, is more expensive. Germanium. Silicon is much cheaper. So we do have germanium. It's the other way around. So we have germanium detectors also. No, silicon is less. Silicon is sand. It's SiO2. Which is yeah, germanium is a lot more expensive. So we do have germanium detectors. Some people work on this stuff. Maybe cost. So now we need to. So each of these.
What I was saying is
Yeah.
very complicated. The T square multiplied by e to the power minus 48.
Yes, it's very sensitive. It's very sensitive. So you have to keep it very close. If you're slightly off the boundary, it will start to like shoot up. It's like this, the function. Right? Yeah. So as I'm saying, so these readout chips they dissipate about 3 watts. You can see, we can think about a 10-watt bulb. Okay, it's still quite a lot of energy. And in order to keep it functioning, you have to keep it at minus 20 degrees Celsius. So you can think about the tremendous, and this is just one chip. There's thousands of these. So how will you keep the whole thing at minus 20 degrees Celsius? So the way we do it is by pumping mixed phase CO2. So basically carbon dioxide that is at the border of being liquid and gas. Using the latent heat of vaporization of carbon dioxide, there are tubes that are going right under the chip that are taking the heat away from the chip. Okay. So this is a very design problem. Okay. So here is, for example, an exploded section of the substrate on which we are putting the chips. So these green things are the chips. You can see it is lying on this thing called carbon fiber. So are you guys familiar a little bit with carbon fiber? I think it's now a pretty hot topic in aerospace industry. It's basically fibers of carbon, and they have very high thermal conductivity. Okay, and the reason we are using carbon fiber and not metal, can anyone tell me why we don't just use copper? Why? What will happen if you have a copper or something in this high radiation environment inside LHC? It will get irradiated. It will get irradiated like crazy. It will also block all the particles who are coming out, right? You cannot have copper. So you have to have a low nuclear cross-sectional materials. And so that's why we are using carbon. Anything to do with carbon is fine. So that's why you have carbon fiber. It has high thermal conductivity, pretty high structural strength, not as much as steel copper, but still pretty good. And it has low nuclear cross-section. And then you can see there is a cooling tube out there. These contain the carbon dioxide, it's going right there. And then there is carbon foam. There is foam made out of carbon also. And that is taking the heat away from these chips to the pipes. And this is the cross section. So this is like the chip. Okay. It is attached with some sort of grease onto the carbon fiber, attached with some sort of adhesive to the carbon foam. And then the carbon foam is also attached with some stainless steel pipe to the mixed steel. Stainless steel is the only unavoidable part. You have to use stainless steel. Okay. So then what we have to do is we have to run simulations to see which is the thermal bottleneck. There will be a thermal bottleneck here. So ultimately what we found is all the components are great. Guess which is the most problematic component in heat extraction? The glue. Okay. Because if you think about it, the glue, it's a polyphenol ether. It's a insulating substance. Okay. So you can have great carbon fiber taking away heat. You are having great carbon foam, all these fancy things. But if your glue doesn't conduct heat, you're dead. So we have to run many simulations of these studies, and we have to come to a conclusion that basically these glues have to be made with 1 watt per meter Kelvin thermal conductivity. And this is a high design challenge. The reason I'll come to that in a second. So it's very difficult to make glues at such a high thermal conductivity. Okay? Because glues are basically resins. So we started on a huge project of this glue. So there are more constraints. The glue cannot disintegrate with radiation. That is another one. In fact, if you use any commercial glue like dendrite or something, see what happens if you put it in a high gamma radiation. It will basically become talcum powder. It doesn't survive at all. So the glue that we got, the original glue, is from Japan. Why Japan? Fukushima, nuclear reactors. They need these sort of things over there. But what they don't typically need is heat extraction. They don't need it to be so thermally conductive. So they gave us a glue. The glue was not thermally conductive. So we have to do something else on the glue to make it more thermally conductive. And we'll come to that later. But here is an apparatus that our students you can see these are basically student-made apparatuses. And they can measure the thermal conductivity of any substance. And this is absolutely a tabletop experiment, where the students design this from scratch. And that's what I'm telling you, I'm trying to inspire you that handy physics doesn't always mean like you have a big, CMS or you can do small experiments and contribute. So this is a simple thing. It's very easy to understand also. So the sample whose thermal conductivity is being measured is put in the middle of 2 copper rods. Each copper rod looks like this. Each copper rod has 6 thermometers inserted inside it. It's called them thermistors, okay? And on the top of the copper rod, on the top is the heater, on the bottom is a Peltier cooler. So basically we have set up a thermal gradient from the top to the bottom. And in between we are inserting the sample. So if you know the thermal gradient over here and you know the thermal gradient over here, you can infer what the thermal gradient across your test sample is. If you know the thermal gradient and if you know the heat flux going through. So the heat flux is in watts. Okay? So you can also infer the heat flux from here because you know the heat flux going through the copper, because you know the temperature in the copper, you know the temperature getting in the copper, and you know the temperature, you know the heat flux coming out also. So So you know the heat flux of the material, you know the temperature difference across the material. Using these two things, you can compute what the conductivity is, thermal conductivity. But of course, it seems always like a very simple thing. It seems like, oh, I can do this like 1 month. It's not so easy. Because there are many things that can go wrong. First of all, big question, how will you mitigate the convective and radiative losses from the sample? The sample is like exposed, right? So how do you mitigate that? One way to mitigate is of course to use vacuum as much as possible. But again, that has its own problems. If you start to make a vacuum with a slight vacuum leak, there will be a draft inside. Okay? Now you have cooling inside, which you didn't want. Okay? So it's a very complicated problem. So basically we have to like tweak, we have to make sure that the heat flux going in is equal to the heat flux going out. If the heat flux going in is equal to the heat flux going out, that means the sample is not losing anything. So that's one way to mitigate heat flux. Okay. Then the next thing is, how do you eliminate the contact conductance from your sample to these copper blocks? You are putting the sample in between two copper blocks. What about the interface? So in order to do that, you have to make multiple samples. Okay, and then take it out as the intercept. So let's move a little faster. So here's, for example, what the students will typically do. So these are mainly higher undergraduate students and even some grad students participate in this. So here, for example, is the 12 thermistors that are taking temperature data. On the x-axis is the time, y-axis is the temperature. Okay, so here's, for example, the red hot thermistors, and then there will be the cold thermistors in the bottom. And you can see the gradient in the hot flux meter on the top and the gradient in the cold flux meter from the bottom. Okay, and so from this, the students will infer that the heat flow through the sample is 5 watts, 5.5 watts. The temperature difference across the sample is 17 Kelvin, and therefore the resistance, which is basically equal to the temperature divided by the heat flux, is 3 watts per meter Kelvin, something like this. And so then they will repeat it for like 5 different samples, okay? And with 5 different samples. So if we actually plot the resistance of this sample as a function of the thickness of the sample, you can totally eliminate the interaction, the coupling constant. Okay, and you can get the bulk conductivity of the material. And for example, here they mentioned something here, 2 watts per meter Kelvin for the carbon fiber. So in the carbon fiber, we have to optimize using a huge campaign. So these are a lot of fun missions. So here's the module mounted grease that I was talking about. The grease had to be thermally conductive, electrically resistant, radiation resistant up to 1.5 gigarads, reworkable, low mass. We had no commercial solution, we had to engineer one. So this is like a resin choice made by Cornell. So here we have to talk with chemists. Why polyphenol ethers will survive radiation? It's basically because there are a lot of benzene rings. And if you think about benzene rings, the electrons are sloshing around in the benzene rings. sp2 hybridization. So when the X-rays hit there, the electrons just do this. Okay, they don't dissipate into like there's no polymer linkage breaking. Okay, so all these things you have to think about.
Sorry, this is carbon fibers are insulating.
No, this is glue.
Is that they're insulating or?
It's carbon fiber is more or less insulating. Yes. You mean thermal insulating or electric?
Thermal electric.
So thermal is conducting. Thermally conducting, electrically is insulating.
But there are next now after the discovery of graphene.
Graphene, yes. Those are very expensive carbon fibers. Those are like graphene, like that much graphene like costs us like $1,000.
There is another one which is fullerenes.
Fullerene, but
They might be cheaper. They might be.
those are carbon nanotubes. No, those are even more expensive. Those we have talked about it with commercial people, and usually we sell them when we are doing LNC stuff. Most people say so.
No, I was thinking maybe one can think of conducting carbon.
So carbon fiber is the closest you can get, but yes, but you can make fullerene like buckets to fullerene also. Those are very expensive. So we took this glue, okay, from Japan, and we had to increase the thermal conductivity. So what did we do? We added diamond dust into it. Okay. So diamond dust people think is very expensive. Actually, it's not so expensive. Guess why? Because diamond dust is used for optical grinding of spectacles and all. So if you go to an optician's warehouse, they actually have very precisely granular, like if you tell them 20 micron diameter, they'll give you 20 micron diameter. If you ask them 5 micron diameter, they'll give you 5 micron diameter. And then there's some very interesting percolation theory you can do. in which you can actually mix different sizes of diamonds, 20 micron diamond plus 2 micron diamond. What we have found, if you mix these two, the percolation theory shows that you get the maximum thermal conductivity. So this is like a very cool kind of physics, like you use chemistry, Haney physics, percolation theory, practicals of buying and selling things.
Yeah, actually, see the glass, actually the thermal conductivity of plastic materials is very high.
Yes. Yes.
So
diamond
side, this side.
Yeah, so diamonds is much higher, like 1400 Alright, so we're coming close to the thing. Okay, so even how do you measure this diamond? Like, so this is basically glue. Glue, you can think like dendrite with diamonds inside it. Okay, it starts to become very thick. But how do you measure this? You can't put this dendrite between the two copper blocks. Finished, the experiment is finished now. It will get stuck. So we basically take sapphire discs and we put the glue inside the sapphire discs to like very well defined thicknesses. Okay, and then we make multiple samples with multiple thicknesses. And then we measure. So, in fact, so this is a picture of the diamond infused glue. So this is I think 30% diamond with a 70% diamond in here. And so you can see that the thermal conductivity of the actual glue before the diamond was 0.2. As you had 33% diamond, it went up to 0.3. As you had 70% diamond, it goes up to about 0.9 was million Kelvin. And this was basically a target. We needed to hit that. So at 70% diamond, we had sufficient thermal conductivity to ward off thermal runaway. And it was also spreadable under the chips. Just spreadable. And then of course the final test was take this glue and put it in a radiation environment, see if it dies. And then we saw that it actually survives. Okay, so this is before radiation, which was 0.9. After radiation, it was 1.03. It was more or less within uncertainty. So we bulk irradiated the samples and also like irradiated the samples themselves with the sapphire test. And we found that we finally made a material. So this is just one strand of a story in high energy physics. And you have to focus on one strand, and this is the simplest strand I could find. And with that, I'll come to the end of my talk with the conclusion. So the conclusion, the CMS experiment discovered the Higgs boson in 2012. And as I'm trying to show you that you only need basic understanding of special relativity and some statistics to begin to make physics analysis contributions, to join high energy physics. It's not like you have to understand all of QFT now before you start doing the analysis. Okay? And also the story of the Higgs is actually far from over. We just started measuring the precision properties, so there's a lot of work to be done here. Also the phase 2 upgrades in the CMS experiment are ongoing, and there exist opportunities to contribute using desktop experiments just as much as with state-of-the-art fabrication hardware. So anyone can contribute as of right now. So with that, I end my talk.